So let's talk about the stellar graveyard. So far, we've seen that low-mass star end up in planetary nebula, and then white dwarf, and then we just talked for high-mass star. We just talked about neutron star. So let's do a review of all those celestial objects and what are they associated with. And what are their dimension and what are they made of? So we already seen that low-mass star end their life in white dwarf, which is pretty much a rock of carbon. We've seen that high-mass star end up their life in neutron star, which is pretty much a rock of neutron degenerated from iron atoms. And so the neutron star are formed from high-mass star, mostly between 8 and 20 mass of the sun. Now when we talk about the most massive stars, more than 20 times the mass of the sun, those ones usually end up in black holes. So in here, let's talk some more about neutron star, and we'll dive into black hole for the next videos. So here is the stellar graveyard, which some images of the sun for scale. So here we only can see a portion of the sun and the size of Earth relatively to scale. We've seen that a white dwarf is about the size of Earth, but a lot more massive. A neutron star is even tinier, but contains a lot more mass. A black hole, it's something extremely massive, but take very little space. So let's learn more about the neutron star. Neutron star, they are remnant object from high-mass star. Inside of them, they most likely have liquid interior, mostly made of neutron, just because the pressure is so intense that inside of the star you kind of have like a soup of neutron. And then they have a solid crust also made of crystalline iron. And they have a diameter of about 20 kilometers. So 20 kilometers, it's less than the distance from Monsac campus to downtown. So that can give you an idea of the size of those objects. Like for example, on the next slide, here I have an example with the campus of the University of Colorado. So it's something like very small, a neutron star. And usually they have the size between 10-20 kilometers and a mass between 1 and 3 times the mass of the sun. If a neutron star reach a mass more than 3 times the mass of the sun, it's usually the breakout point where it's going to become a black hole if it's too massive. And we know that they spin rapidly. So let's see what happened here. So everything has to do with the conservation of angular momentum. Remember we talked about that when we learned how solar system was formed when this cloud of dust and gas called the solar nebula starting to collapse. So its radius was getting smaller, but the mass was the same. The radius was smaller, mass was the same. So to conserve the angular momentum, to keep it the same, we needed the velocity to increase. So we observe this for everything rotating. When something collapses, and in this case if we talk about a neutron star, then if the radius is smaller because of the collapse, the velocity needs to increase because in the universe everything is transformed. It doesn't appear out of the blue. So if you decrease a quantity, you need to increase another one. Like for E equal mc squared. If you decrease the mass, you need to transfer it somehow into energy. So here is the same thing. Neutron star spin fast because they are shrunk. Their radius is so small, but the mass so great that you need to have them spin. So that's an observation that was made by Jocelyn Bell at Cambridge while she was a graduate student, and she discovered it by accident. She was observing a star, and she saw sign of a rapidly spinning star that she originally named the little green man, because it was like a signal sent by an extraterrestrial. And as you can see, sadly, like in history, so her director received the Nobel Prize for the discovery, but her name was never mentioned. So that being said, she is really the one discovering what we call the first pulsating neutron star. So let's look a little bit more about like a real case in the Crab Nebula. So the Crab Nebula is the remnant of a supernova explosion, which it means that was a high mass star that reached the end of its life. The outer layer bounced back out of the core, that's what you're seeing here, and exploded. And at the center of the supernova, you have a neutron star, the remnant of the star. And so observing this star at the center of the Crab Nebula, you can see a pulsating effect. Every 0.033 seconds, the stars become brighter. So how do you explain this? You explain this by a star spinning extremely fast. And what we think is that there is jets of light that emanate from these stars, and what we see is the star being a little bit like a lighthouse. The jets are out of the pole, and as the star rotates, sometimes the jet is right in front of you, so that's when the star appear very, very bright. And once the ray of light passes, the star dims a little bit until you are again in the path of this ray of light emanating from the pole. It's really work like a lighthouse. And we also know that those stars, those neutron stars, are very magnetic. So we know it has something to do with the magnetic field that intensifies those rays of light, those beams of radiation in the universe. So those star is what we call pulsar. A pulsar is a rotating neutron star. So Jocelyn Bell was the first one to discover the existence of a pulsar in the universe. And so a pulsar is a rapidly rotating neutron star. Now there is a saying. We can say that all pulsars are neutron stars, but not all neutron stars are pulsar. So something we're not sure of is we think that every neutron star might have those beams of radiation, but we can't see them if the beam is not projected in our direction. If you never go in the path of those light of beam, if the pole of the neutron star is not toward Earth and Earth, then we can't really know if they are present or not. So those pulsar stars represent the portion of neutron stars that are perfectly aligned with Earth for us to see their beam of light, their beam of radiation at every time it goes in Earth direction. So that's why we say every every pulsar is a neutron star, but not every neutron star is a pulsar. So neutron star is formed. So that's what this is saying. We cannot always say that it is a pulsar because it depends on the orientation of the neutron star magnetic field, so of the orientation of this beam of light. And so we've been using pulsar beam as galactic pointer to our location. So this one was a plaque crafted in gold, sent on spacecraft, Pioneer 10 and 11 spacecraft that have been sent through the outer solar system. And so in this plaque, we represent human. Here is the sun, and here those lights represent direction from different pulsars that we can see. So if extraterrestrial were to encounter the Pioneer spacecraft and to read this plaque, we hope that they would be smart enough to understand that those are a pulsar beam that would indicate our position in the solar system. So now to finish on neutron star, we've seen for low mass stars that white dwarf can be in binary system, while if white dwarf can do it, so can neutron star. A neutron star are found a lot of time also in binary system, and so there is, as for the white dwarf, there is mass transfer of mass between a supergiant and a neutron star, and usually this end up with a lot of X-ray, intense emission, and explosion. And neutron star can also sometimes collide with each other. It's very rare, but we have at least one observation of it, and that's what causes what we call gravitational wave. It's about one of the most massive supernova explosion that leave traces throughout the universe through a wave from this huge explosion.